Okay. Hello, everyone. So we are finishing up the notes from section 4.2. So make sure you put these problems in your notes. And the example, I want to do 2 examples and Rolle's theorem. So 3 examples in total. Okay. All right. So this first example, and if you want, you can stop the video and write it down, and then come back and listen to how we're going to solve this. Okay, we need to find the max of f of x equals 1 minus the quantity x minus 1 to the 2/3 on the closed interval -1, 2. Okay, and so, excuse me, remember, since we're on a closed interval, our theorem tells us that we will have our max and our min will be on a closed interval. We always have a local max or local min. And additionally, those values will either be the endpoints on the closed interval or the critical points. Okay, so the first thing we want to do then is find the critical points. And so step 1. All right, so we're going to find our critical points. So that means we have to take the derivative of our function and set it equal to 0. So looking at this function right here, we have 1, and the derivative of 1 is just what? 0, right? So 0 minus, and then I'm going to use brackets or big parentheses, the derivative of x, the quantity x minus 1 to the 2/3, that's actually, we're going to be using chain rule, right? Because there's 2 functions there, and we can use the power rule property for chain rules. So this will give us 2/3 times x minus 1 to the 2/3 minus 1, which is -1/3, times x minus 1's derivative, okay? But as we can see, this derivative is just going to be 1, all right? So, but I wanted to show that because I want you to get into the habit, make sure you're comfortable with using chain rule, okay? So then if we simplify this up a bit, f prime of x equals, and so I should have put an f prime of x there, it equals -2 over x minus 1 to the 1/3. Okay, and so all I did was, since that's to the negative, I brought that down. And here's a nice little fact, so you might want to write this down just to remember for my class and future classes. If you have x to the negative n, that will equal 1 over x to the n. Okay, and so that's all I did. And I'm missing, what am I missing? Someone should realize what I'm missing. I'm missing my 3, right? That 3 is in the denominator. Okay, so -2 over 3 times x minus 1 to the 1/3. Okay, and so we found our derivative. Now we have to take our derivative. So now we need to set f prime of x equal to 0. Okay, so we take -2 over 3 times x minus 1 to the 1/3 and set it equal to 0. So we multiply both sides. So this is just some algebra. You should really know how to do this already. So if not, you want to really make sure you review your algebra skills, simplifying fractions and things of that nature. All right, and I'm just going to do it for this video. I won't do it for future. So those go away. The left-hand side, we have -2 equals 0. Well, this will never happen, right? This will never happen. So in regards to finding a critical point by setting our derivative equal to 0, we have no critical points, right? However, remember the definition of critical point says C is a critical point if f prime of C equals 0 or f prime of C doesn't exist, right? So now we need to go back and look at our derivative function. Look carefully at this, x minus 1 to the 1/3. Okay. And we need to see, is there anything bad about this? So I want to really take a little bit of a minute and on the side, so a little aside, and you can definitely put this in your notes. When you're asked to see if where a function does, what values does a function what values make the function bad? And bad, I mean, if you put in this number into your function, you won't get an output. It does not exist. Okay. And there are 3 main areas you look for. All right. And so I'll probably talk about this again, but I want to mention it here. The first are if your function has a denominator. Okay. Right? Because we know in our denominator, we don't want our denominator to equal what? 0. So we have to, if our function has a denominator, we have to look to see when does that denominator equal 0. The second is if we have even roots, because we know for even roots, it has to be greater than or equal to 0. We can't have negative because we're not talking about complex numbers. So we can't have negatives in our roots. We can't have negative numbers under our radicals. Even radicals, it doesn't matter. You can have a negative number. The cubic root of -1 is -1, right? Because -1 times -1 times -1 is -1. Okay. And the third one is log functions. And you may remember this from calculus. For log functions, your inputs cannot be negative or 0, right? Because nothing raised to a power will equal 0, and nothing raised to a power will equal a negative number. Okay. So if you have those three things, either those three things, one or more, then you need to look to see where you're going to have. You could possibly have some bad points. If those three conditions aren't in your function, then you know your domain is good and you won't have any bad points. Okay. So for us, looking at our function, I'm sorry, I covered up that too, but looking at our function, we have a denominator. So we need to know what will make that denominator 0. Okay. Okay, so again, we have this, and you don't have to rewrite it. I'm rewriting it because I had to start a new page on my iPad. All right, so here we look to see what will make it 0. If you see it straightforward, then you can just go ahead and do that value. But if you don't see it, you just set your denominator equal to 0 and solve. Equal 0, so divide by 3. So x minus 1 to the 1/3 equals 0. To undo that 1/3, you take the cubic root of that on both sides. And I'm going through this kind of fast because this is just some algebra review. And so you'll be left with x minus 1 equals 0, so x equals 1. All right, so that means, and you sort of could have solved from this function that denominator. If you plug in 1, that's going to make that whole denominator 0. Okay, so that's what, if you see it straightforward, you don't have to go through the process of setting the denominator equal to 0. So thus, c equals 1 is a critical point. Okay. Okay, so now we compare our values at our critical points and our endpoint. Well, we just have one critical point, so that's 1. And then we have our two endpoints, right? And so check this. Don't just write down my answer, but I actually want you to check this because I could have made a mistake on purpose or not. But anyways, check to make sure you get for our critical points, and it should work out. We have for 1, f of 1 was 1. F of -1, it was sort of an approximation, so about -0.59. And f of 2 gave us 0. Okay, so looking at these functions, we need to find the maximum on here. And so that's why this table is really nice, because once you complete the table, it's clear to see where your max is. Okay, so the max is at 1 when x is equal to 1. Okay, and here's a graph of the function. Remember that our critical point was our undefined point, right? It was because our critical points are where when we find the derivative, we set it equal to 0, or where the function does not exist. So if one of your critical points is a point where it does not exist, that means you either have that sharp V, like in an absolute value in your graph, or the cusp that I was talking about yesterday. So in this example, we have the cusp for this particular function. So this is how that function looks. Okay, so now what I want you to do is look at and write examples 5 and 6 from section 4.2 in your notes. Make sure you understand them. And if you have any questions, you can see me during office hours or email me. But make sure, or send a message on GroupMe, make sure you understand those two problems and how they receive their answers. I'm going to stop this video and then start another video with the last theorem and do an example, and then we'll be done.